So to continue, we had reduced that trigonometric integral to this rational integral over the unit circle. And there are only two residues that we care about, the residue at minus 1/2 and the residue at 0. So we do the partial fraction expansion of this rational function and use the cover-up method or any method you like. But for example, we cover up z equals z plus 1/2 here, and we plug in z equals minus 1/2, and we do the arithmetic and we get 3/4. For the one at z equals 0, you have to do a self-checking step, or you can expand in series and you get 1/2 over z squared, which we don't care about, minus 5 over 4 over z, which we do care about. So the residue at minus 1/2 is going to be 3/4, and the residue at 0 is going to be minus 5/4. And I didn't even bother to figure out what the coefficient of this over z plus 2 is because, well, that's outside the circle, so I don't care. So the residue at minus 1/2 is 3/4, that's that guy, and the residue at 0 is minus 5/4. And so the total integral is minus 1 over 4i times this integral, and the integral is going to be 2 pi I times the sum of the residues. So 2 pi I times the residue at 0 plus residue at minus 1/2. So canceling the 2 and the 4 and canceling the i's, we get minus pi over 2. And then we have minus pi over 4 plus 3 over 4. So that's minus 2 over 4 times minus pi over 2 gives us plus pi over 4. So this is correct. This is the correct answer. We can check that Wolfram alpha. If we ask Wolfram alpha to do the original trigonometric integral, it says, sure, the answer is pi over 4. Raises the question of why you have to know this, but we'll talk about that in class. It's a useful trick in a lot of circumstances, but actually it's just cool to know for this particular thing. So the main trick is that this integral is much easier in the complex plane than the original integral was over the real line. If you want to integrate sine squared over 5 plus 4 cosine theta, you have to do some interesting tricks. You could try substituting for 5 plus 4 cosine theta, but then you lose one of the signs and you get square roots of ugly things in there, and it becomes actually even worse to deal with. You can use the Weierstrass tan theta over 2 substitution. This one is actually easier. And you notice that we didn't find any antiderivatives. We just computed some residues, which is really derivatives. So this is the opposite way of finding integrals. Instead of finding antiderivatives, we find derivatives. And that is enough to tell us what the value of the integral is. Okay, thank you.